Hello everyone. It's my honor that you are joining me for this presentation. I'm delighted to be here to talk to you about species distribution model SDM using R software. As a matter of fact, the issues of species distribution is mostly used in forest science, and its modeling helps in predicting the future of the species, and its good position currently. The function of this model is based on the presence and absence of data. One of the goals of this model is to find the optimal habitat for the species considered. My presentation is divided into 9 parts. Let me briefly introduce myself. My name is Laya Zeinali. I'm PhD candidate at Rladies University. I'm searching in forest remote sensing and modeling. I'm interested in the climate change issues and ecosystem services. And my thesis is about these topics in Hyrcania forests in north of Iran. The Hyrcania forests are one of the ancient forests in the world that are left over from the Ice Age. These forests, with an age of 25 to 50 million years, is considered one of the most valuable forests in the world and is referred to as a natural museum. The area of this forest is 55,000 square kilometers, and it's among the richest ecosystem in the world, with high biodiversity and unique characteristics. Some of the trees that exist in the Hyrcania forest have more than 5 to 10 million years of genetic evolution. In 2019, with the efforts of respected professor this faculty, headed by Professor Said Mohsen Hosseini, it was registered in the UNESCO World Summit. As I mentioned, SDM, the function of the model is based on the presence and absence of data, or a presence-absence of the species. One of the goals of this model is to find the optimal habitat for the species in question. In addition to the presence and absence of the species, environmental data are also required to perform the model, including topographic data, slope, direction, and height, soil and climate data. The raw data is entered into R software. After converting it into the data, we get the final output during the processing stage and reach to information. The total number of environmental variable is 19, which is prepared based on the average rate of the precipitation, minimum, maximum, and average temperature for 12 months of the year. In general, the data are divided into 2 categories, spatial and non-spatial. Spatial data is divided into 2 categories, vector and raster. Vector, including points, line, and polygon, and raster is a pixel-based. Descriptive data is also included in this category. This step to perform the work, at first we call a record package such as RIO, SF, and raster. RIO for import, export, and convert data files. SF is a standardized way to encode spatial vector data, and raster geographic data analysis and modeling. We will continue to use SP, SF linked by SP for classes, and method for spatial data. First step, we can use 2 methods to load our data into the R software environment. In the first method, you can use the RIO package with this command. After run this command, open the window and we can choose the data file. This windows. Second method, it's possible to set the working directory. Working directory set from this command set wd. Using the list file command, list.file, you can see all the files in the folder and then select the desired file from this command and show these windows. Our data was in Excel with XLSX format. Using both methods is possible, and the result is the same, and our data file is added to the software environment. Second step, we use the SF package to convert the data into a spatial object, which we call it at first this command. With this command, we convert the existing data into spatial data so that we can work with them. In this command, the data are the same data that were already entered into the software environment. Coordinates are the X and Y columns of our data, and CRS are the latitude and longitude. Geographical references coordinates system define points on the Earth's surface with the help of longitude and latitude values. These values are the angle measured from the center to the Earth with zero longitude located on the given meridian. According to this form, our data has been converted into spatial data. These numbers, which noted below, the command line for converting spatial data indicate the zones inside the country Iran is located in the 4 main zones, 38, 39, 40, and 41. And the last 2 digits of each node number it indicates the intended zone, which is mentioned above is zone 38, 39, and 40. By using 2 commands, data.sf and data.sf extend, the following details can be seen. Now, to find out where our data is located, use the map view package and call the package with the library map view command. Purple point in the map indicate the absence, and the yellow point indicate the presence of our data or our species. By zooming and clicking on each of the data or each of the point, you can understand their details. In a map, the 3-dimensional ground is displayed in 2-dimensional form and needed can be converted using different models. Each model position in the format coordinate are described within a references coordinate system. After click on the points, we see this information. Our spatial object may be constructed using the SF or SAP function. To switch between these 2 functions, we use the following command. Convert SF to SAP with this form with this command, and then convert SAP to SF with this command SAT underscore as underscore SF. In this image, show that we have switched from SAF to SAP. After executing this command, the same coordinates were obtained according to the following tables. SAP function must be used to the above command and reach to this table. Remove identical coordinates. We have used this command. After removing the identical data with the following two commands, it can be seen that 13 of our data that had duplicate coordinates were removed, leaving 2,717 data out of the 2,730 data. Now it can be seen that we don't have data with duplicate coordinates. After performing the above step, we return to the data from SAP to SAF again from last comments. Next step is mapping. To prepare mapping, we need different maps, including environmental maps starting from bio 1 and ending bio 19. In the next step, we enter environmental maps from 1 to 19 into the software with the following commands. The above command is repeated for all 19 maps. Dim map, elevation, slope, and direction can help the reach to final map more. Finally, with the stack command, all 19 layers are combined, and the next step are perfumed. For the convenience of work, there are maps called multiband, which have all 19 environmental maps aggregated in them. For the above topic, if the raster command is used, only one band will be displayed. But with the stack command, you can see all the bands. All 19 bands can be viewed using the names command. To change the name of each the bands, we hand some the following commands. Finally, we get the following output. Next step, uploading the shapefile of Hyrcania region. Using the following commands, we add the map of Hyrcania region to the software. From this command, using the following commands, we draw the diagram of the Hyrcania region and add points to each. By executing these commands, the map of next slide will be obtained. The next step is to import the DEM map. We add the DEM map to the software using the following commands. This segment gives us this information: class, dimension, extent, CRS. In the next step, we cut the bios and the DEM map for the northern area. And finally, we perform masking. We perform the cutting operation using the following command. By placing the Hyrcanian maps on the above map, the following map is obtained. For this purpose, we use these commands. These commands run respectively and reach to this map. And finally, with the mask command, the extra part of the above map are cut and only the desired area remains for this purpose. The following command is used. The previous steps are repeated for the DEM map, and the following map is obtained. Finally, you can reach the masked map with the following commands. The next step is to add the slope and direction map. We run this command respectively. Slope is calculated in percent of direction in degrees. Then we use a solar radiation index using the following commands. Then we use the following commands to access the display mode. According to the obtained values, which are between 1 and 0, the number 1 indicates the south and southern direction, and the number 0 indicate the north and northern direction. Next step, stacking the map we made. Run this command. The image showed that 22 maps, 19 environmental maps, DEM map, slope map, and orientation map are stacked on top of each other. Next step, matching all above information for each point. For this purpose, the extract function and the following command are used. The name to data SAP2 was used because we had data with the same coordinate. Data.sap with the same coordinates, and we removed them. In the next step, this information is placed next to the species information. In this picture, for each of our data, in addition to the information we had from the beginning, the information of 22 other maps has also been added. Next step, examining the collinearity problem. Using the SDM package to fix the collinearity problem when there is a correlation between the variables. Use the above command to fix this problem, specifying those whose VIF is greater than 10 are identified. We may repeat this VIF determination for several steps to get the desired result. According to the above table, 14 of our 22 inputs had problem, and those that remain have a VIF less than 10 are shown at the bottom of table. Then we run this command and receive these informations. The next step is modeling. The logistic regression model. This model is used when our data is 0 and 1, presence and absence. This command includes the presence and absence of the species and the value of the environment variable that are not collinear. The reason for using this case is that it's used for the binomial distribution. Data is binomial. Using the summary GLM command, those that are not significant are identified. It's clear that bio-8 and orientation direction were not significant. After specifying the above step, we remove those that are not meaningful from the model. In the image on the previous page, it's clear that bio 8 and orientation were not significant. For this purpose, we use the mass package and use the following commands respectively and reach this information after running the final model with the summary glm.final command. All significant variables are obtained as shown in the following image. And the last step, preparing the final map. Preparing the final map based on the glm.final model, the predict function is taken from the raster object is a variable that we stacked. Finally, we prepare the final map with the following command. Finally, the R software uses this formula and generalize it to the entire area and gives us the map as presence and absence. With the following commands, the final map is obtained as follows. These maps, then the place marked with a yellow color are very likely to be absent, and the places that are purple have a low probability of species presence. The final map is run using the following commands. Run this command respectively and reach to this final map in the Hercanian forest. I'd like to end my presentation here. Thanks for coming, and if you have any more questions, I'd be happy to answer them afterwards.
Thank you, Laya. It was a very great event. We learned a lot. Nagme, do you want to say anything?